Algebra 2, Lesson 5.9, Write Polynomial Functions and Models. We are going to have two main examples today, the first of which is when you're given points of the function and you have to write the equation that passes through all of those points. Now these points won't be random points. The first 3 points will be what we call the zeros of the function. In other words, those are the points where the polynomial crosses the x-axis when graphed. You've just been given the x-intercepts. So the format is going to be very familiar to intercept form of a parabola that you learned in lesson 410 and worked more with back in lesson 4.2. So let's set it up in what looks like intercept form. Intercept form would say your function is equal to a times x minus one of those x-intercepts, in this case negative 2, times x minus another x-intercept, in this case negative 1, times x minus the third remaining x-intercept. Clean it up, and your function is going to look like a times x plus 2 times x plus 1 times x minus 1. Again, this format is very similar to intercept form of a parabola that you learned about in lesson 4.2 and lesson 4.10. Look back at your notes and you'll see that the process we're going to do right now is the same thing we did in those previous lessons. In addition to being given the intercepts, we're also being given another random point on the graph, the ordered pair 0, 6. We are going to treat this ordered pair as the x and the y, then in essence will go in place of x and y in the equation. We're going to look at our function notation, the f of x, as if it was the y equal to, and I'm going to substitute 6 in place of the y and 0 in place of x everywhere to give us our new equation. Just follow your order of operations. You need to take care of what's in the parentheses first. Here you'll have a 2, there you'll have a 1, there you'll have a negative 1. So it's 2 times 1 times negative 1, negative 2. So your equation changes to 6 equals negative 2a. Next you'll divide both sides by negative 2. Now you know what the value of a is. Your final answer is the function after you've substituted negative 3 in place of a. Your function is equal to negative 3 times x plus 2 times x plus 1 times x minus 2. Again, when you're writing the cubic function, meaning your biggest exponent will be a 3, you'll have an x cubed, you will have 3 x-intercepts. Your polynomial will cross the x-axis in 3 places. In addition to those 3 points, you'll also be given another random point that the function, when graphed, goes through. Let's take a look at another example of a different kind of problem. In this problem, the ordered pairs that you're given that your polynomial would go through when graphed are not the x-intercepts. There are 4 points that are on this polynomial. So we're going to use a technique called finite differences to help us figure out what our answer should look like. It'll help us figure out the format that we should be using. When we evaluate finite differences, you're going to be given multiple ordered pairs. Here's an ordered pair 1, 1, ordered pair 2, 5, ordered pair 3, 13, ordered pair 4, 25. But when evaluating finite differences, we're going to just list the y's first. 1, 5, 13, and 25. And then we start working backwards. And we're subtracting, just like the word difference implies. I'm going to take 25 minus 13, that gives me 12. Take 13 minus 5, gives me 8. Take 5 minus 1, that gives me 4. All 3 of these numbers here in purple are different numbers. You will need to go through the finite difference process one more time. What's 12 minus 8? 4. What's 8 minus 4? 4. Once you have all the same number after you've completed your finite difference, you can stop with the subtraction. What's important to note here is that The number of times you have to do the finite difference process, that tells you the degree of the polynomial that is your answer. Because we had to do finite difference process twice, our answer has a degree of 2, meaning it's going to look like an ax squared plus a bx plus c. That's the format of our answer. We are then going to take the ordered pairs that were given to us and substitute them in place of this equation. Because there are 3 unknowns, A, B, and C, we don't even need to use the ordered pair 425. It was important to have that while we worked on our finite differences. But because we only have 3 unknowns, we only need to have 3 equations in our linear system. Each of these equations was created by taking, in this case, the first ordered pair, the 1, 1. We're going to put 1 in place of x everywhere, and it's equal to the y value of the point, which was 1. For the next equation, I'll put 2 in place of x everywhere, and that equation will be equal to 5. Lastly, I'll put 3 in place of x everywhere. This equation is equal to 13. Next step would be to clean up the equation. Square any numbers that can be squared. Now that we see these 3 equations with our 3 unknowns, A, B, and C, we can create a coefficient matrix and solve this linear system using matrices. So the coefficient matrix will pull the coefficients of each of the equations. First equation has 3 coefficients, 1, 1, and even the C has a 1 with it. Second equation has coefficients 4, 2, 1. Third equation, 9, 3, 1. So we will set up a matrix, our matrix A, with the coefficients. We will then multiply that times matrix B. Matrix B is what each equation is equal to, the 1, the 5, the 13. When you multiply A's inverse times B, you'll get a matrix with 3 numbers that represent your 3 unknowns, A, B, and C. In this case, we get that A is 2, B is -2, and C is 1. But that's not your final answer. We want to write the equation of the polynomial that goes through all those points we saw on the previous page. So we will now substitute A, B, and C into our function notation, that our answer is the function 2x squared plus -2x plus 1. Let's try one more example. Here are our ordered pairs. We will now start subtracting the y's from right to left. 6 minus 21, -15. 21 minus 22, -1. 22 minus 15 is 7. And 15 minus 6 is 9. We need to do the process again. Be very careful with your subtraction. You're going to have -15 minus -1. Minus a negative is adding a positive. We still do not have all the same number on this last line, so let's complete our finite difference process one more time. -14 minus -8 is -14 plus 8. We get a -6. -8 minus -2 is -8 plus 2. We get another -6. Because it took us 3 times, that means our polynomial has a degree of 3. Our biggest exponent is going to be a 3. So this right here is the format of what our answer is going to look like. It's going to be an ax cubed plus a bx squared plus cx plus d. So now we have 4 unknowns. We need to find A, B, C, and D. So we will need to use 4 of those ordered pairs. We don't need the 5, 6. It was important to have it during the finite difference process, but now because our equation has 4 unknowns, I'm only going to need to use 4 of those ordered pairs. So I'm going to carefully substitute each ordered pair into my format, clean each equation up, and now I can write my coefficient matrix. My coefficient matrix, the first equation has all 1s. Second equation, your 2 cubed is 8, 2 squared is 4, 2, and then a 1. Third equation, 3 cubed is 27, 3 squared is 9, 3, and then a 1. 4 cubed, 64. 4 squared is 16, 4 and a 1. You will set this matrix up as A, set the second matrix up, which each equation is equal to, as B, and take A's inverse times B. You will get A, B, C, and D. Make sure you put them back into the format to see that your final answer is the function negative 1x cubed plus 5x squared, that should be superscripted, plus 1x plus 1.